So if you have your general chemical reaction, that we're used to seeing, right? That we were writing some stoichiometric amount of A plus balanced amount of reactant B going to C plus D. We've seen this many times, okay? Let's go ahead and suppose that these are redox. So suppose these are redox half reactions without the electrons drawn, right? Without the electron transfer being shown. So then we can write them. Let's go back and write them as half reactions. It might be something like this. Whatever the stoichiometric equivalent we need of the electrons is. I don't know which species in the generic equation are getting and receiving them, but this is one possibility. So then go ahead and recall that when you want to calculate the free energy change of a reaction, so sometimes you'll see this with superscript reaction or with just the letter R. It is the standard state free energy change plus, we have to add what's going on with our actually observed concentrations of stuff. So products over reactants. Same as always. We called this piece Q the reaction quotient. And these were observed values of our species reacting, not at equilibrium. We're never really at equilibrium. We said in real life in the cell, we have permanent concentrations of certain things that we're maintaining that are not 1 molar, right? So then we had written earlier on the last sheet of notes we wrote a relationship that looked like this. It was negative delta G over dF. Before this top piece, we just had the equilibrium piece in there, okay? That was that RT over the natural log, or not over, I'm sorry, RT the natural log of equilibrium constant. And we also have this piece of information here, right? Well, I mean, it came from this, I'm sorry. I wrote a lot of notes and didn't rewrite them pretty, and I'm trying to write them prettier now. And I haven't planned exactly what I want them to look like. But that's a rearrangement. So then, if we want to get the the potential difference at some non-standard state condition, okay? This would be equal to the standard state potential difference, okay, minus the natural log of, let me just write Q in here for now. Let me try and say this again. If we're not at standard state anymore. Now I'm just looking at the free energy change. This piece is this whole piece here. So I could write this as negative delta G minus RT. I've just put my Faraday's constant times the number of moles. I've just put it through on the bottom here. Okay, so this top piece is here. This is what we just wrote up here. And all I've done is I've put my negative nu times Faraday's constant through on the bottom. And that is how then I can rewrite this as just standard potential. That was a little rough of an order, but does it make sense for people? I'm going to write it one more time. if you want to calculate a potential difference not at standard state. It's the standard potential difference minus some term for your actual observed concentrations of everybody. And this is called Nernst equation, or is one form of it, okay? And what it basically lets you do is it lets you determine a change in voltage or a change in potential difference of an electrochemical cell as the concentrations of the reacting species are changing, okay? So this is going to let me determine a change in voltage, which we said another word for that might just be the change in potential difference. We can use these interchangeably. Of my electrochemical cell as the concentrations of the reacting species change, which they do in that cell. Our copper zinc one, for example, we keep losing solid zinc into solution, okay? So the zinc ion concentration is going up, the concentration of solid zinc is going down, and on the other side is the reverse situation for copper, right? As this current is flowing, we're changing the concentrations of what we have, right?